this video, I'm going to focus on position versus time and velocity versus time graphs for objects that move with constant velocity. Let's look at an example. Here this red cart is moving to the right along this horizontal track. The position versus time data shows that every 2 seconds the cart is moving exactly 1 meter. Because it's changing its position at a constant rate, this is an example of constant velocity. If we were to graph this as position versus time, we'll get a nice linear graph shape. And now we want to write a mathematical model that supports this graph. Because the graph is linear, I can analyze it with y equals mx plus b. My y-axis variable is position x, so I'll sub that in. My x-axis variable is time t, so I'll sub that in as well. And I can use the data to find the slope and y-intercept as 0.5 meters per second and 0 meters respectively. But what do these numbers mean? Let's look at a few examples to try to make more sense out of them. Here we're looking at 3 carts placed on a horizontal track. Notice the positions they're placed at, and they are stated to never move. What would a graph of position versus time look like if we were to analyze these carts sitting still over a time of a few seconds? Well, our position scale is the y-axis. I'm starting with 0 at the origin and counting up 1 meter for each tick mark. I'm starting red at 0, blue at 2, and orange at 3. You can see where they're placed. And because they'll never move, well, these objects will be at their respective positions for the entire time frame. So we get 3 horizontal lines. Next example, we have 2 carts moving to the right. Notice they both start at a position of 0. Red is moving slow with respect to blue that is moving faster. If we were to graph both of these on the same position versus time graph, how would their lines look? Well, they both start at the origin, 0 meters. Blue is going to have a steeper slope than will red because blue is covering more position per time interval, being that it's the faster object. Our last example, let's place a cart over there to the right at 4 meters, and we're going to have it move backwards to the left towards 0. Well, this cart would not have a y-intercept of 0. It would have a y-intercept of 4 meters, and it's going to move downward back towards 0 meters. So we can have a negative slope for this graph. That just means we're moving in the opposite direction. Our goal was to make more sense out of the slope and y-intercept. Well, now we can conclude the slope as being the instantaneous velocity. We know this because it's measured in meters per second, and the slope can be positive or negative, which is a better connection to velocity than would be speed. Our y-intercept is the starting position. It is the position value when time equals 0 and is measured in meters. To summarize, for position versus time graphs, know that the y-intercept represents the starting position of the object. The slope of the line will represent the instantaneous velocity of the object, and the acceleration value will be 0 for all objects moving with constant velocity. Let's now look at a second type of graph. This is the velocity versus time graph. The origin is in the middle, representing a velocity of 0 meters per second, or an object that is not moving. Data in the positive quadrant contains positive velocities, so those are objects moving forward. Data in the negative quadrant has negative velocities. Those would be objects moving backward. A few examples. Here we have a ball placed on a horizontal track, and the ball is stated to sit in place. So if we were to graph it as velocity versus time over a time of a few seconds, this velocity would always be 0, so we get a horizontal line at the origin. Now let's have the ball move to the right. Because it's moving from 0 to 1 meter, that's moving in the forward or positive direction. It's increasing its position by positive 1. So this object has a constant positive velocity. I'll put a horizontal line somewhere in the positive quadrant. If instead I'm graphing something moving to the right with a faster constant velocity, I would need to make the horizontal line further up on the y-axis, but still in the positive quadrant. Next, let's look at a ball rolling to the left with constant velocity. It starts at a position of 1 meter and ends at a position of 0, so it's changing its position by negative 1 meters, or moving in the negative direction. I'll have to move my horizontal line into the negative quadrant because that would be a negative velocity. Finally, let's look at a sample problem. Here we have actual numbers to use. We have a constant velocity of 2 meters per second for this ball, moving to the right, and it's going to move for a time of 3 seconds. First goal is to graph the motion as velocity versus time. We would scale the graph to find where positive 2 meters per second would be and draw a horizontal line at that velocity. Next, we want to find the displacement. I can think of 2 ways to do that. The first would be to use the average velocity equation from our previous talk. We know the velocity is always 2 meters per second, so that would serve as the average as well. And we're doing that for a time of 3 seconds. Using the equation, I get a displacement of 6 meters. Something else to point out is to analyze the area underneath the graph line. If I shade in this area, I wind up with a rectangle, and I can find the area of that rectangle with base times height. The base is 3 seconds, the height is 2 meters per second. Finding the area would also give me an answer of 6 meters. So it looks like the area under the data of a velocity versus time graph is another way to find displacement. To summarize velocity versus time graphs, know that the y-intercept represents the initial velocity of the object, the area underneath the data represents the displacement of the object, and another reminder that acceleration equals 0 for objects that move with constant velocity.